We are starting the last and the third presentation during the Warsaw Self-Driving Cars. I'm just telling to the people who will be watching this, because this will be the one and only presentation which is recorded and shared. So welcome, and Maciej Dziubiński will show you how to create a top view image from 4 cameras around the car. So it's similar to systems that you have in your car, maybe already. That you have 4 cameras and you have top view, so you can easily navigate. But this will be done entirely in end-to-end neural network. Am I right?
Almost.
Oh, okay. Sorry.
Almost. Yeah. Okay. So, hi. My name is Maciej Dziubiński. I work as a machine learning engineer at a company that specializes in fraud detection. This is not related to autonomous cars in any way, so this is a side project of mine. Yeah, and you might notice that the title is a bit different than the title given in the meetup. It's because there's also a blog post, and if you Google this exact title, you'll be able to find the blog post. I also included a link in the upper right corner. You can check it out. So I'll be talking partly about things that are already written in the blog post, and partly about things that can be done or things that didn't work, and I didn't want to include them in the blog post because who want to read about failures? So yeah. So maybe before I jump into the agenda, let me show you what's the problem. First of all, I'm working only with semantic segmentation. I'm assuming that I have semantic segmentation from somewhere, and the problem at hand is to take the 4 cameras that are mounted on the car to produce the top-down view, again in semantic segmentation, of a camera that's hanging, I think it's about 50 meters above the car. And the question first is, can we train a neural network that can do this, and also what kind of assumptions there are hidden in the neural network so that it works. Okay, so going back to the agenda. So first, the motivation. I'll say a few words about the input and the output. A few more words than I've said already. And I'll mention the Carla Autonomous Driving Challenge, which was actually the inspiration for this project. It's an ongoing challenge. Carla is a simulation environment if you're interested for autonomous cars. I use it very often because it's very useful to get the data that it's very hard to get from a real world, and also perfect data, right? Because I have perfect semantic segmentation here. And to test out ideas and to have this very nice environment in which everything works, everything is fine, because in robotics the default state is nothing works, nothing wants to work, and you have to struggle with that, and in the simulator everything is just fine. So that's the motivation. Then I'll jump into discussing the architecture of the neural network that I actually use for creating this top-down view, and then I'll say a few words. Why would anybody want to use this top-down view, or I call it bird's eye view? Yeah, that's the whole presentation. So first, let's focus on motivation. So you've seen this already. This is the problem. We have an input, and this is what we want the model, which is a neural network, as I said. This is what we want to predict. This is what we want to model. Right. So the first obstacle is that you might not see it in this particular example, but there are problems where a car is somewhere in front of our car, and we don't actually see what's behind it. So we're sort of assuming that the neural network will somehow be able to extrapolate from the data that's around the car, that's obscuring view, what's behind it. So that's one problem. The second problem is that those cameras, I've used cameras that are specified in the Carla Autonomous Driving Challenge. They don't cover the whole 360 degrees angle around the car. There are actually regions, mainly here and here, which are not visible in any of the cameras, because the first camera is like front, those two cameras, they overlap, and the rear camera, it doesn't have a field of view that would include the whole view. So there is a part of the scene that's not actually given as input. So again, the neural network has to extrapolate or maybe generate this output, figure out this output, guess this output. I'm not sure. Generate is a good word, but I'm afraid that you might think that I'm using a generative model. It's not actually a generative model like a generative adversarial network. It's just a normal neural network. Yeah, and just to one more sentence. Notice that there are parts of the input that can influence any given part of the output. And I didn't want to hard code the information that, listen, this part of the input should somewhere here contribute to the output. I didn't want that. I wanted the neural network to have no such constraint and to be able to figure that out on its own. Which imposed some difficulties. I'm not going to go into the details. If you want to ask later on, I'll be happy to explain. Okay, so the Carla Autonomous Driving Challenge. It's an ongoing challenge where you have, the task at hand is to go from point A to point B. And there are 4 different types of data that you can use. And those 4 different types of data, they are actually 4 so-called tracks. And you can win in each of those tracks separately. And there are prizes in each track separately. But you can just focus on one of the tracks and do your best. I'm not going to discuss all of the tracks, but we'll be focusing on track 2, where you have RGB cameras as input, those 4 cameras that you saw earlier, but actually it's not semantic segmentation, so actually RGB. So you would need to have a neural network for semantic segmentation to actually use the model that I'll be presenting here. Yeah, and there are 3 other tracks. In particular, the fourth track is the simplest, well, let's say simplest. The simplest one because you have all of the data given to you on a silver platter. You don't have to deal with the sensors. You have all the information about the pedestrians, the cars, and everything. And I think traffic cars as well. And all you have to do is plan the trajectory of the car and maybe predict the trajectories of other cars. Well, anyway, so it's the simplest one. And I think if you want to take part in this competition, you can still do it. And track 4 is, I think, requires the least amount of work. Okay, so let's say that we're focusing on track 2. We're using only cameras, like Tesla, let's say. And the challenge here is that there are different types of scenarios in which your model needs to perform adequately. So, for example, from my perspective, the hardest ones are situations where you have to predict that there will be a pedestrian on your path, and a scenario where when you're losing control over the car, meaning that there is a slippery part of a road, and you have to maneuver your way out of a dangerous situation. The other scenarios are typical, I would say. So it's not that hard. But those 2, I think they are the hardest, and especially if I were to use my approach. From my perspective, it's very hard to notice that there will be a slippery road or that there will be a pedestrian on the road. But anyway, part 2, how to train the neural network. Okay, so this is the architecture. It might look a bit complicated. But there are 2 important parts on which I want you to focus on. The first part is that in orange, I have a decoder submodel, and I have an encoder submodel. Actually, those 2 models, even though on this diagram they are very far away, they are actually 2 parts of a autoencoder, a fully convolutional autoencoder, which takes as input any of the images, the left camera, right camera, front camera, rear camera, and also the camera from the top. And what it does, it reduces the, let's say, dimensionality of the image, and then it decodes this image and it recreates the image that was given as input. But for my purposes, I use that encoded image to then build on top of that a stack of dense layers, a separate stack for each of the inputs. So for the front camera, the left camera, right camera, and rear camera, each of those cameras has its own stack, which is trained separately. Then I have a convolutional layer, then I concatenate those outputs, then I have another convolutional layer, and then what I do is I put this representation into the decoder submodel, which was trained to recreate the image. And that's how I get my reconstruction. That's how I get my my top-down view. And obviously, I don't get all of the information that are required to project how the top-down view will look like. But here are the results.
Can you go back to this?
Excuse me?
Can we go back to this model?
Yep.
Because first thing you do is flatten, and I don't understand why you flatten, because you lose the spatial relationships.
Exactly. But I'm doing that because I want to have this relation every part of the input. I want this property that every part of the input influences every part of the output. If I didn't do that, and if all my whole model would be a fully convolutional model, then notice that in a fully convolutional model, what you actually get is a given part of the input can influence only a given part of the output. There is no way. There is a way. I'll talk about that later. There is no way for let's say right upper angle of the input to influence the left lower part of the output. So somewhere in my architecture, I need to have this way of allowing the neural network to have an influence of any part of the input to every part of the output. That's why I have this flatten. And yes, I'm losing information with that. And I'm not satisfied with this architecture. Just to say, just to explain myself. I'm looking into other methods of dealing with this, and I'm very open to suggestions. And yeah, we'll have a Q&A for that later. Okay. So yeah, this is the architecture. Here are the results for 7 classes. So those are road, pavement, vegetation, vegetation I think, cars, buildings, sky. It's actually none. It's not a class or something like that. Sometimes we have sky on the ground, so that's a tricky part. But anyway. So yeah, so this is a 7-class example, meaning, I have these 7 classes, and it means that some of the classes are really not visible in the input. It's very hard to guess them. So for example, rooftops. You don't see a rooftop. You have to guess, or rather the model needs to guess where the rooftop ends. So this is how the results look like. Maybe we can go full screen?
Yes.
Okay, so the rightmost image is the predicted image, and this is ground truth. So you can notice that it looks a bit psychedelic, and also the cars, they seem to appear from nowhere, out of nowhere. The car is very far from our car, or rather, other obstacles are very far from our car, but we notice them very, in a very, let's say, narrow time window before our car. This is actually because the representation here is using this trick of predicting a class according to the highest probability provided by the model, which is an argmax, basically. So actually, the model does predict that there is a car, but the probability is very low. And notice that cars are a very rare class, and because of that, there's a bias that the probability of a car being there is very, very, very low, from the baseline. Okay, so
the representations are fed separately, or can you merge all of the inputs?
Yes, they are merged. Yes. In the architecture there was a concatenation. Here, this is the concatenation that merges all the.
Before that was separately. I mean, in the encoder part.
Yeah. So I didn't get it.
I mean, the encoder part model.
Yeah.
You have a 4 input. Yes?
Yeah.
Or 1 input. 4. And when you give it to the model.
I get 4 encodings. I flatten all of those. there is a single box here because it means that there's a single model for all of the inputs. They are actually going, all of them are going through the encoder and then...
Like core
no, in the encoder, there's only one encoder.
Or instances of...
There are 4 references to the same model, actually.
Yeah.
So yeah. Okay. But in reality, if you want to drive, you only need, and not bump into other cars, you need 3 classes. Car, road, and everything else, right? Maybe pedestrians, probably. But no, pedestrians are not important. I actually didn't focus on pedestrians, I just, excluded them from the simulation. I wondered how the model performed if there were pedestrians. But anyway, this is how the 3-class model looks like. Again, there's this problem of cars reappearing out of nowhere. But in reality, because there is some probability, because there are only 3 classes, you have 3 layers, you can actually encode this, because I'm showing you the argmax representation. You can actually use those three layers and give a RGB representation, and then you can see those cars, and they are actually predicted, although with a low probability. And that's something I'm going to show in a second. But before that, there was this question, or sort of question, why didn't I use a fully convolutional neural network? The one that you use, for example, for semantic segmentation. And the reason is because a given part of the input influences only a given part of the output. There is a way of dealing with that. So, for example, in this particular brain structure, right? Suppose it's a 3-dimensional. Because we have 3-dimensional convolutions. But in any case, this part of the input can influence only this part of the output, and so goes with all other parts. And that's one of the reasons why I didn't use a UNet, because this in particular is a UNet architecture. But there's also a second reason why I didn't use in this particular case, a UNet. There are those so-called skip connections, which greatly enhance the accuracy of the model. However, no. Excuse me. Okay. Yeah. So, to be honest, I have no idea how I can those skip connections. How can I incorporate those skip connections into my my model for producing this top-down view? I'm open to suggestions. I'd like to talk about it more. So yeah, that's why I didn't use the fully convolutional network. And there were other ideas to use a fully connected neural network. So take the image, use the structural information, the spatial information, flatten that whole image at the entrance, and then stack a set of layers, dense layers. And I used that. The problem was that the results were even more wobbly or psychedelic. And the model that I presented earlier with the convolutional parts was much better. There is a way of using a fully convolutional architecture. The trick is to use a filter on the bottleneck, on the encoded representation, to use a filter that's big enough to be actually able to encompass a large portion of the encoding. I actually used this to the extreme. I used a filter that's actually the shape of the bottleneck, which was like 12 by 18. I've never used a filter that's 12 by 18, but I used this filter and I did get better results. But the results that you see here are not from that architecture. The problem was that I actually didn't have a lower number of weights or parameters of the neural network because there were still some problems, and I used a lot of those filters. I actually, I just checked if it worked, and it did work, but the model was probably too large to. Was too large. It was larger than needed. Another idea are non-local neural networks. Here's a paper from 2017 from Facebook, which uses so-called non-local interactions on the image. I had to dive into that. The number of weights is greatly reduced, and the idea is to look for patterns in the input. Look for pieces of the input that are actually the same. So, for example, in the three-class case, most of the image is actually the other class, right? So it's a huge waste to use each pixel separately for that class. You can try and visualize, or rather capture some patterns that occur throughout the image. And the fourth idea is to use generative models for the unavailable regions. So in the cases where other cars obscure the view, and also when you don't see, for example, the rooftop. I'm guessing a generative model would do a better job than the model I'm using currently, but I haven't tested that. And I haven't tested the local neural networks, so I tested the first two. Okay, so why would anybody use, or rather, why would anybody need this top-down view? So in the blog post, because I felt that there is this, this gap that you have no idea why would anybody use it, I presented, or I rather proposed a very simple control algorithm. And this is the RGB representation. So now blue are cars, and you'll be able to see those cars from afar, but with a very low probability. This is a very simple algorithm which takes a step and then looks around for it goes where the road goes. So it's able to maneuver around other cars and is able to follow the road. This is how the results look like. On the left you have ground truth, and on the right you have the predicted waypoints. So it's able to drive around other cars, more or less. There are situations in which the waypoints, they cannot make up their mind. And it's basically because I'm not actually driving according to those waypoints. I haven't tested that with an NPC or any other controller. I actually just ran it on the test set that I used to assess my model. But it seems to be doing okay. Maybe the slight problem is that you don't get as you don't see that far in this representation. So there are problems where you don't, where you go fast, you'd rather see what's much further in front of you. So that's one possible application. That's not what I wanted. But there are other applications. Okay, thank you for your attention. Just a moment. There are other applications. You can use this representation for a reinforcement learning algorithm in which you can use the feedback that you get from Carla, because Carla gives you information about whether you crossed a line, whether you entered the pavement, whether you bumped a pedestrian or another car. So it's great input for a reinforcement learning algorithm. But the difference here, compared to a information where you just get what you see here, what you get from the problem, is that you can train a reinforcement agent that has a more, it actually has a bird's view eye. So the agent, the model that you use, assuming that you're using a model-based agent, the model might be, for example, an MPC with parameters, and those parameters are being tuned. So you have an MPC, you follow the waypoints. The parameters of the MPC might be tuned according to the rewards that you get from driving, following those waypoints, for example. So a reinforcement learning algorithm would be a good application. Yeah, and also I'm guessing that because I'm using semantic segmentation, if I had 4 cameras with semantic segmentation and with a model for semantic segmentation in the real world, and I could mount those 4 cameras on a real car, I would actually have the model for producing a projection, a top-down view, and I might try and drive a real car on a real road. Yeah, but that's a discussion for a different topic. I don't have those 4 cameras. But the fact is that we can mount those cameras in whichever manner you want on a real car, then project that into the simulator, then train a neural network for getting the top-down view, then perhaps getting the waypoints and trying to drive a real car around in a city. So yeah, so that's another application. Yeah, so thank you for your attention. I don't want to talk more. If you have any questions, then please ask them. If you'd rather ask in Polish, then go ahead. I can answer those too.
I have one question, actually a few questions regarding the resolution input to this neural net.
Yeah.
Actually, these four inputs, what was the
resolution
of the image and the output resolution?
Yeah.
And the second question was how many training? What was the training set? How many examples?
Okay, so I didn't want to go into those details, so thanks for the question. The input was, the size of the input was for each camera was 150 by 100, and the output was also 150 by 100 but transposed, meaning that you have like this, and the input you have vertically, horizontally, and you have output vertically. And how large was the input? The input was composed of 40,000 images, but maybe 40,000 times 4 input cameras and top-down cameras, so 40,000 frames of a simulation. It was very hard to gather those data because I was sitting down with the gamepad and I was driving around. And the problem was that in this gaming engine, there is a cutoff, meaning that objects that are far away, they are not actually rendered. So because the camera, the top-down view camera was very far, the engine actually excluded everything. So I had to, I had to tweak the threshold in which everything was generated. And as a result, the gaming engine had to render everything in the town. So it didn't run very smoothly. It ran like 10 FPS. Yeah, so gathering data in that conditions is hard.
One remark from me. You can, theoretically, you can record the path without any cars, or maybe with the cars around you, and then render training set after. So you are driving recording without rendering objects that are far from the car. So you are just you can
play. You can render that post.
Yes.
Oh, that's a neat trick.
Everything.
Yeah. You can try that.
I have one more question. And the input was the binary data, or it was the probability output of this segmentation model?
I didn't use a segmentation model. I'm assuming I would be able to train a good model for segmentation.
Yes, but the output from the segmentation model could be the level, or the probability of the class.
So if I used a model for segmentation, I think I would go with probability. And not the argmax, because that's more information. You're just losing information if you take an argmax. To be honest, I tried a end-to-end model in which you get RGB as input and semantic segmentation as output. However, the classes, if you don't use skip connections like you have in UNet, you don't get very good results. You get a huge blob. Every car is a huge blob. The road is more or less okay, but the blobs are too blobby. Yeah. I think that if you use skip connections, you might have an end-to-end model, but to be honest, I have no idea how to use those skip connections thus far.
Interesting question for this is if it will be faster than classical approach with computer vision.
Oh, meaning a homography.
Yeah.
But homography is, for example,
Anti-point.
and what?
Anti-point matching.
Point matching. I didn't know that one. But I'm not sure if classical approaches they can extrapolate what's behind a car. But
assuming that you have full 360 around the car.
Yeah, and also those projections, I think often they assume that the chassis of the car is stable, which is not the case when you drive really fast because everything moves. And I was actually driving very fast because I wanted to gather as diverse data as I could. And
in the simulation, the car behaves dynamically, or?
Yeah.
Okay.
Sure. Yeah. Okay. Any other questions?
Actually, regarding the ground truth data, the segmented top bird's eye view, was it something that was provided by the simulator, or did it?
Yeah, it's provided by the simulator. You actually get semantic segmentation, depth view, some other information are probably extractable. You can get the velocity of objects. I'm not sure how it's that called. Is that the heat map? Whatever. You can get a lot of information from the simulator, and this is from the simulator.
And another question is, how much time do you need to compute a single frame of this output?
Actually, the inference is very fast. It's very fast. It's 40 milliseconds on a GTX 1080. So I have no idea how long it will take on a Jetson or.
Yeah, but you have small images.
Yeah, the images are quite small, so that's not an issue. And I didn't optimize it in any way. I'm assuming that if you use TensorRT or whatever tool for optimizing those architectures, you'd get maybe 10 times faster inference. The problem was with training. Actually, each training session took about 28 hours, which for my modest possibilities is like it almost killed the project because I need this GPU for other projects. So in order to run this, I was assuming that I'm going to use the whole night. But then when it turned out that I need 28 hours, my first thought was, okay, I'll try this one time, the full training set, and if it doesn't work, I'm dropping this project because I had other things to do. But it worked, so I ran several training sessions. Okay, any other questions? Okay. Thanks.
Yeah. We still have 5 minutes before the start. So, anyone want to ask about this project or? Okay. No? Okay. So thank you very much.